Hello, my name is Savannah Ramsey. I am in 8th grade at Southeastern Junior High, and this is my second year in Science Club.
Hello, my name is Amanda Stevens. I'm in 8th grade at Southeastern Junior High, and this is my second year in Science Club. And the name of our project is Feeding the Future, investigating the symbiotic relationship between tilapia and tomato plants in an aquaponics system.
Before we begin, we'd like to thank our sponsors, Ms. Guyman and Ms. Will, for helping us with our project and guiding us through the scientific method. We'd like to thank all the people that donated towards the project and our parents. And we'd like to thank Southeastern Junior High for having a Science Club program. We'd like to thank Brady Holtz for mentoring us and donating supplies and his time. We appreciate Paul Hitchens and Steve Koss for supplying us with tilapia and teaching us about aquaculture. We'd like to thank Jeremy Stevens for helping us troubleshoot our project and donating supplies. And lastly, we'd like to thank you guys for taking the time to listen to our project.
Aquaponics is a sustainable method for raising both fish and vegetables. You can grow substantially more food with less water, labor, and land than traditional agriculture. Nutrient-rich water from raising the fish provides a natural fertilizer for the plants, and the plants help to purify the water for the fish. Aquaponics has many benefits. It uses a sixth of the water to grow 8 times more food. It doesn't rely on mined or manufactured fertilizers. Its produce is free of herbicides and pesticides. It allows for continuous year-round production, and aquaponics is as sustainable and earth-friendly. The fish produce ammonia, and oxygen comes from the surroundings. Nitrosomonas bacteria convert ammonia to nitrites, which are deadly to the fish. Oxygen is added, and Nitrospirea bacteria convert nitrites to nitrates. The nitrates are nutrients for the plants, and the plants absorb the nitrates and clean the water.
With limited natural resources and an energy crisis on the rise, finding solutions to these problems are essential. Aquaponics is a sustainable farming and gardening technique. It conserves water and energy, leaves a small footprint, and allows for year-round production. The purpose of the scientific investigation was to develop an aquaponics system with a symbiotic relationship between tilapia and tomato plants that allows for both species to thrive. Specifically, pH, nitrates, and nitrites were measured to determine the effect of plant quantity on water quality as an indicator of a sustainable symbiotic relationship.
Based on research and conversations with multiple aquaponic experts, it is predicted that increasing the number of tomato plants will promote a sustainable symbiotic relationship between tilapia and tomato plants. It is hypothesized that as the number of tomato plants increases, the amount of nitrates and nitrites will decrease, creating a healthy living environment for the tilapia.
First, we had to construct our systems. Remove the tops of 5 IBC totes and flip them over for the grow bed. For each tank, we reduced the valves and attached tubing to the pumps to circulate water. We ran the tubing through the grow bed using a hose barb T to distribute the tubing. We drilled holes in the tubings, and we wired the pumps to connect them to the power. We set up the air pumps for each tank and attached the air bubble stone. To secure all the tubings, we used clamps. For each tank, we placed heaters, and we filled them with 700 liters of water. We plugged in all equipment into power sources. After the tanks were prepared, we put 2 tilapia in each tank, all equal weight. For each day, we would add 20 grams of fish food to each tank, and we turned on the air pumps and heaters. We monitored the water daily with aquarium test strips for 35 days prior to adding the plants to allow the microbes to build up and the nitrification process to start. Our project had many challenges, and this was probably one of the biggest ones. We did not anticipate how long it would take and how hard it would be to allow this process to start. It required a lot of daily care. We would determine if the water needed change and the pH would need adjusted, and we would do so if necessary. We use this chart to help us decide, and for each component there's 3 levels: a safe, ideal, and water change. To change the water, we would remove 350 liters of water and add 350 liters of fresh water. To adjust pH, we added 30 milliliters of white vinegar, and on the last 7 days, we recorded the results in the data tables. For adding the plants, we placed 6 pots into the grow bed portion of the 5 tanks. We added 7.5 liters of perlite in each pot, and we would transplant the 1 tomato plant into each pot in tank 1, 2 plants into each pot in tank 2, 3 plants in each pot in tank 3, 4 plants in each pot in tank 4, and 5 plants in each pot in tank 5. We secured tubing over the tops of the plants to irrigate the plants with the water from the tilapia tanks, and we turned on the pumps to begin cycling the water. We turned on the grow lights and set a timer. For testing, we used aquarium test strips, and we measured the nitrates, nitrites, and pH. Each day for 20 days, we would measure the water levels, and we would record them into our data tables. We lastly averaged our results and calculated standard deviation using Microsoft Excel. This is an example of 2 days that we tested the water. Our first picture is an example of a day we did not need changes, and these two first pink squares are the nitrate and nitrite levels. All the levels are stable, so we do not need to change. And the second picture, the level on the last tank is much higher, so it required a change.
Our independent variable, the one thing we changed, was tomato plant quantity. 6, 12, 18, 24, and 30. And our dependent variable, the one thing we measured, was water quality. Nitrites, nitrates, and pH. And our controlled variables, the one thing we kept constant, was system setup, growing environment, tilapia mass, tilapia care, aquarium test strips, and scale.
Now, here are our tables. Each day, we measured the nitrate, nitrite, and pH levels, and we recorded if there was a water change or pH adjustment. We did this over a 20-day period. We then averaged all the results over the period of time for the nitrate, nitrite, and pH levels. We totaled up the number of water changes and pH adjustments, and we calculated standard deviation on all 3 components to see the results in the variation in our results. Here is our first graph, the total number of water changes. Along the x-axis is the number of tomato plants, and the y-axis is the number of water changes. As you can see, tank 1 with the least amount of plants had the highest number of changes, and is followed by tank 2, and 3, 4, and 5 had no changes. They had stable levels. Our next graph is the average pH. Across all 5 tanks, the pH levels are the same, and they had very little variation. In this graph is the total number of pH adjustments. Again, all 5 tanks had the same number of adjustments, and this indicated that the number of plants did not affect the pH in the project.
The main reason we watched pH closely was because the tomato plants cannot tolerate as high as a pH as the tilapia can. We do not want the pH to get over 7.6 because the tomato plants prefer a more acidic environment.
And our next graph is the average nitrates. Again, the first tank had the highest levels with an average of 52.5. It is followed by tank 2, and 3, 4, and 5 all had stable levels. There is a significant difference in the levels in tank 1 and then the levels in tank 3, 4, and 5. And we knew this because the bars for the standard deviation do not overlap. Our next graph is the average nitrites. Again, tank 1 is the highest levels, followed by tank 2, and 3, 4, and 5 were all stable.
The reason there is so much variation in tank 1 and 2 is because we had to change the water for the safety of our fish. If we did not change the water, the nitrogen levels would continue to rise. And this also shows you that tank 1 and 2 do not have a symbiotic relationship. It was predicted that increasing the number of tomato plants would promote a sustainable symbiotic relationship between tilapia and tomato plants. After conducting testing, it was determined that the hypothesis was supported. It was hypothesized that as the number of tomato plants increased, the amount of nitrates and nitrites would decrease. As expected, ammonia levels decreased as the plant quantity increased. It was concluded that the 2 tanks with the least amount of tomato plants were not a sustainable system due to the fact healthy water quality was not maintained, potentially harming the tilapia. Further results will be gathered to determine if plant quantity affects the plant productivity.
Effort was made to conduct this project in a controlled manner. However, some variation did occur in the results. We had no control over the individual health of the tilapia or tomato plants. The range on the test strips was higher than desired, and the project relied on human eye to determine the results. Overall, our project did show consistency. Thank you for listening to our presentation.